Hello, physics students. Hey, welcome back to another edition of Rapid Review for Honors Physics. Today we continue our discussion of waves, and we're going to get into the concept of modes and harmonics. Let's get right into it. First, I'll start with a review, right? You remember that we have transverse waves and longitudinal waves. We learned in an earlier episode that there are various possible modes of vibration for a vibrating string. We looked at the various conditions, whether it was constrained on both ends or maybe open on one end and closed on the other. And it begs the question, could you get those kinds of things? Could you get standing waves in a longitudinal wave? And of course, my answer is yes, because otherwise this would not be a very interesting presentation. Check it out. This person here is creating a longitudinal wave with a long stretched spring. And even though I don't show it yet in the picture, what's about to happen is some of those pulses will hit the wall on the right side of the picture and they'll bounce back. So you'll get reflections. They'll interfere with the original wave and create conditions that might create a standing wave. And if you remember, what's required to create the standing wave is we have to vibrate the spring at just the right frequency. So let's take a look at how and when that happens. We're going to use, instead of a slinky, we're going to use a hollow tube. So that's represented schematically here. I'm going to outline it in green. That's a hollow tube, and there are particles of air represented by the dots, and we're going to allow air particles to move left and right in the hollow tube. Notice that the hollow tube has a dead end at the wall, so there will be some reflections of any wave activity that we might generate. What would happen in that tube? Let's look at this schematic diagram, and I am so sorry, but I actually, in drawing this, I reversed left and right compared to what we were just looking at. So now the closed end, as you can see, is on your left side. So hopefully that does not cause any confusion. I would now have you consider what's happening at the different ends. Air can easily move on the right side, left and right, because it's open to the room ambient pressure or atmospheric pressure. The left side, there's not a lot of room to move. It is possible it's going to get squeezed in there. That could be a location of some higher pressure. In fact, rather than talk about pressure, I'll use displacement. There's a footnote here regarding pressure, but I will speak about displacement here and note that we have a displacement antinode on the right side because the air particles are free to move left and right, and a node on the left side. So you'll notice that this is starting to look a little bit like a vibrating string, except now we have a longitudinal wave instead of a transverse wave. Okay, so how many modes are possible? Well, it turns out many, right? As long as you have the constraint where antinodes are on one end and nodes are on the other, you can see there are various modes, right? And I'm only showing 3 of them here, and they relate to particular lengths as a function of lambda, and no surprise, these are the same modes we saw earlier, right? So for a vibrating string, the harmonic series is quarter lambda, 3/4 lambda, 5/4 lambda, and here we are in an air column with the same harmonic series. So all of the math is the same for a vibrating air column as it is for a vibrating string. Now I find, and I think students find, the longitudinal waves harder to visualize. So to help with that, I'm proposing that you look at an animation. I'm not going to run it here in the presentation, but I point you to that animation and I will link to it. It's basically what we just looked at, plus a piston on the left side. It's moving back and forth, left and right, at some frequency f. And so it squeezes and stretches the air next to the piston. right? And you can guess that if I move that piston at just the right frequency, I should get a resonance, right? So let's see what is just the right frequency. It's, oh, I didn't say what resonance was, did I? Let me show you. Okay, so there's a notion of resonance that is when you put energy into a system, it might respond in various ways. Here's a system. It's a mass on a spring. We've seen this before. I'm going to put energy into it by giving it just a little nudge with my hand. You can see my hand moving. And if I do that at some particular rate, I'm using a metronome here to suggest to me 80 beats per minute. Let's try it. You can see that nothing much interesting happens in the system. But if I try a different frequency, I'm going to change my time now to something, this is about 58 beats per minute. This is something I already know is the resonant frequency of this system. Let's check it out. Watch what happens. You can see it goes nuts, right? Why does that happen? It's because this system wants to vibrate at its resonant frequency. If I put in some other frequency, it doesn't much care. It doesn't react very much. But if I put in something that's at that resonant frequency, it reacts. This has big meaning in sound. If I take a tube that's, say, open at the top and closed at the bottom, you might have done a lab where you had a water level plugging up the tube at the bottom, and so you get a length that I'm showing here. That's L, right? Oh, that's terrible, but you know what I mean. You can have an air column, and if you make it vibrate like that piston at just the right frequency, you can create standing waves in it. For example, if you wanted to get a standing wave where L is 1/4 lambda, you could find the frequency that would be required to create that resonance. And in the lab, you'll take a tuning fork. If I could wiggle my hand, like if I could wiggle my hand over the top of that tube, I would be able to create some resonance at that, just like I wiggled my hand over the mass on spring. But instead, you will wiggle your tuning fork above the tube, and it's going to move back and forth much faster than I can wiggle my hand, right? So that's how you put energy into that system. You create a resonance. You can create various modes in that system, right? So if you do it, you can figure out, let me see, I'm going to pause here. Yeah, you can figure out what frequency you need to get resonance. Okay, now I gave you the fundamental harmonic, L is 1/4 lambda, and if you calculate that, spoiler alert, you'll find out that you need to adjust your length to match your tuning fork by adjusting the length to 33 centimeters. Other modes are possible. I'm not going to get into that here, but you could use other lengths that resonate at 3/4 lambda or 5/4 lambda or so on. But I'd rather leave you with a couple more problems here. I'm going to ask you to freeze the video, and you can try these on your own. See if you don't get 128 hertz for the lowest possible note that a clarinet can make, given this information. And if you like that one, try problem number 3. This is a real flute group playing with flutes of various lengths that you can estimate from the picture, and you can guess what notes they could possibly do. You can assume that the fundamental wavelength for the flute is 2L, and I won't support that with background, but that is the case for a flute. Okay? So with that, I think we've said enough about resonance. If you want to learn more about resonance in musical instruments, I have a longer form video that I made with my students. I will link to that in the comments. And other than that, I have nothing more to say today about resonance in longitudinal wave systems.